Welcome student, this is video lecture 3 for PCH 280151 Unit 3 Organometallic Chemistry 3. In this third lecture for organometallic chemistry, we are talking about metal alkyne complex, metal acetylene complex, its synthesis, structure, bonding, application, properties, etc. I am Dr. Devanga Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. Transition metal alkyne complexes. Here you can see that alkyne complexes in which acetylene would be the ligand, alkyne, that is R, C, triple bond R, have two mutually perpendicular sets of pi and pi star molecular orbitals. Therefore, the chemistry of alkyne complexes is somewhat more complicated if we compare it with the metal alkene complexes because of a greater possibility of bonding by alkyne ligands. Alkyne can be bound to metal using their one or both set of pi molecular orbitals acting as 2 electron or either 4 electron donor ligand. So here alkyne can play two kind of role for one or both set of pi orbitals, molecular orbitals. It may either donate 2 electrons or 4 donor ligands, and in both probability there should be a different type of bonding with the central metal ion by alkynes. At some time, alkynes may also act as a bridging ligand, binding to the two metal centers simultaneously. So that way it will differ from alkene ligand as well. Alkyne complexes have studied extensively than alkene complexes. However, the alkyne complexes also have some fascinating characteristics which already we have briefed about, donation of electron, differ, bridging ligand, etc. The transition metal alkene complexes can be prepared by general synthetic routes. There we can compare it with alkene as well somewhat. First point would be that one molecule of an alkyne can replace 1 2 electron donor ligand from transition metal complexes, forming corresponding alkyne complexes. So here the alkyne act as 2 electron donor ligand as well. Now these are certain reactions in which alkyne act as 2 electron donor ligand, and substituting a carbonyl, here you can see that hexacarbonyl molybdenum treated with alkyne in presence of UV light, you can see substitution of one carbonyl group from molybdenum by alkyne group will going to get this alkyne complex. Similarly, if we have this complex where only one carbon monoxide ligand would be there and 2 cyclopentadienyl pentahapticity would be there, and it is treated with alkyne, you can see that one carbon monoxide which is there, which is replaced by alkyne group. Similarly, for pentacarbonyl ion complex, it is treated with alkyne, so alkyne going to replace one carbonyl. So all these reactions are similar. Substituting one carbonyl group, alkyne act as a 2 electron donor ligand and can attach with the transition metal complex, forming corresponding alkyne complex. In such cases, only one of the 2 pi electron pair of the alkyne molecules are involved in the bond formation. When we study the bonding, we are going to see the difference of 2 electron donor ligand, alkyne as 2 electron donor ligand as well as alkyne as 4 electron donor ligand. Now method for the preparation. Second route, one molecule of alkyne can replace 2 electron donor. Here alkyne act as 4 electron donor ligand, from a transition metal complex, forming alkyne complex. Here you can see that titanium dicarbonyl cyclopentadienyl bis cyclopentadienyl complex treated with two alkyne here which proton of alkyne is substituted by two phenyl group. So this ligand act as a 4 electron donor ligand, and substituting 2 carbonyl we're going to get the alkyne complex where hapticity is 2. So here dihapticity would be there compared to the previous one. That is how this for preparation method is little different. In this case, both the it's electron, typological mistake. Electron pairs of the alkyne molecules are involved in bonding with metal atom, and it can act as for electron donor ligand. Now in the third method, one molecule of alkyne can replace two bridging carbonyl group of a polynuclear metal carbonyl compound, forming an alkyne complex. So this is how in these two cases the alkyne ligand differs from alkene when we compare and contrast. So here you can see that dicobalt octa carbonyl complex would be there treated with diphenyl alkyne. It's going to substitute two carbonyl group, and especially this bridging carbonyl has been substituted by this alkyne. Same in this reaction as well. Other bridging ligands can also be replaced by alkyne molecule. Here you can see this alkyne molecule where on one side it is substituted by phenyl group, other by methyl group. It's going to substitute trifluorophosphine, 2 mole of trifluorophosphine from this rhodium, and going to give you alkyne complex by substituting this bridging ligand. So that is another method of preparation for alkyne. In such complexes, alkyne molecule act as bridging ligand as well. So it will going to attach with bicenter ligand. So that is how we will going to get the bridging metal alkyne complex, which is different than alkene. Now when we have Fe3CO12 is treated with diphenylacetylene, its 3 bridging carbonyl groups are replaced by 1 molecule of alkyne. You can see the reaction is given over here, and 3 bridging carbonyl is substituted by this alkyne and act as a bridging ligand as well. Here alkyne molecule act as a triply bridging, that is mu3 ligand, and a triple bridging complex is going to be formed. And in the last formation you can see some alkyne complexes can be prepared by reduction of metal halide in presence of alkyne as well. So here you can see that metal chloride substituted in presence of alkyne, reducing agent sodium amalgam is used, and one of the two chloride is substituted by this alkyne, and we're going to get this metal alkyne complex. Further in preparation, the alkyne molecules can replace the coordinated alkene molecules. This is how we substitute the alkene and convert it into alkyne. You can see this platinum complex where triphenylphosphine, bis triphenylphosphine dichloropplatinum complex treated with ethanol in presence of hydrogen hydrate and olefin, we're going to get this complex formation. And this is a alkene complex, metal alkene complex, now treated with alkyne. So the alkene substitution would be there, and we're going to get the metal alkyne complex formed as a bridging ligand. The alkyne molecule have at least one substituent on acetylenic carbon atom, generally from stable and isolable complexes, particularly with late transition metals. The alkyne tends to dimerize to form metal acyclopentadienyl pentadienes, to trimerize to form substituted benzene or to incorporate carbon monoxide to give cyclic mono or diones. We're going to see the example over here for that preparation. These are the example where you can see pentacarbonyl ion of ferrate will treated with diphenyl acetylene, and it will going to form this complex, and then it is treated further with this biphenyl complex, and so we're going to get these three different type of product. Then it treated with the dimethyl acetylenic group, we're going to get this product. And when it treated with 3 molecule of dimethyl acetylenic group, we're going to get this cyclic uh, metal alkene complex as well. Now, to understand the structure bonding in metal alkyne complex, it is little different compared to alkene, where there is a simple kind of bonding. Here there is different. The simplest alkyne complex resemble those of alkenes, that is a simple only 2 electron donor can act as alkene. The preparative route, which are the same route, and the bonding descriptions and analogous, for example in the form of a pseudo 4 coordinate complex, trans platinum dichloropyratoluidine and tertiary butyl acetylenic group. This complex, the alkyne group, is perpendicular to the molecular plane, and the plane of coordination, the tertiary butyl groups are bent back by 15 degree, and the CC bond is lengthened from 1.20 angstrom to 1.27 angstrom. You can see in the structure over here, where this is the phenyl group, and phenylenedione will going to attach over here, bulkier group, and trans to it we have this alkyne, and here tertiary butyl will bend down little 50 degree more, and the bond length between carbon-carbon lengthened from 120 to 1.27 angstrom, and perpendicular it will attach to platinum. So this is as simple attachment as alkene, and here the acetylenic ligand act as 2 electron donor ligand to the platinum complex. Now in other case, such as in a pseudo 3 coordinate complex platinum, in which you can see 0 oxidation state, eta 2 PHC triple bond CPH, that means diphenyl acetylenic group, and 2 bis triphenyl phosphine ligand would be there as well. The alkyne group is almost in the plane, that is 40 degree, and the attached substituents phenyl groups are bent back to an angle of 140, and here alkyne can act as 4 electron donor. As a result of that, hapticity would be 2. It suggests a formulation intermediate between 3 coordinate platinum 0 and 4 coordinate platinum 2. Here you can see the structure formation. Triphenyl phosphine ligands would be there in a planar arrangement, and planar to 40 degree up we're going to get carbon-carbon of acetylenic group, diphenyl group would be there, and CCPH, that is acetylenic bond angle, would be of 140 degree, and carbon-carbon bond lengthened to 1.32 angstrom, and that bond from the plane up increase up 40 degree. So out of the plane arrangement, due to this stress, we're going to observe in this kind of ligand where acetylene act as a 4 electron donor ligand. Now in the structure of the bicentric complex, that is CO2 CO6 PHC triple bond CPH, that is diphenyl phosphine with hexacarbonyl dicobalt complex, the acetylenic linkage CC group lies above and at right angles to the cobalt-cobalt vector, Here the cobalt vector, and above that we're going to get this acetylenic group, and the carbon bond length even lengthened to 1.46 and act as a bridging ligand to the bicentric complex. And the cobalt bond length would be 2.47 angstrom found over here, and this is a bridging example of a bridging acetylenic metal complex, bicentric complex. Now the CC bond is lengthened to 1.46 angstrom, and the cobalt distance is decreased to 2.47 angstrom, where you can see in the example of octacarbonyl di cobalt complex. When you have this rhodium hexa triphenyl phosphine ligand with acetylenic, where one side is methyl substitution and other side phenylic substitution to this rhodium complex, and for nickel complex as a bicentric nickel complex we are going to have the biphenyl acetylenic group, give the similar kind of structure like the above which we have seen. And you can see these two similar kind of structure over here, triphenyl phosphine ligands both the side of the rhodium, and upside we're going to have this acetylenic bond where carbon bond length will be higher, that is 1.46 angstrom. Here as well, here one group is methyl group, here both the group would be phenyl group, and here both the group will be cyclopentadienyl complex, but the structural arrangement is quite similar between these two bicentric complex. And the structure of Fe3CO9 and acetylenic diphenyl acetylenic compound, the diphenyl acetylenic molecule acts as a triply bridging ligand, and the structure you can see where triply bridging ligand, yes, here you can see this one attached with center 1, 2 and 3 simultaneously. So triply bridging ligand, we're going to get this structure. A bonding scheme can be proposed for alkyne complex similar to those proposed for ethylenic complex. The acetylenic carbon is sp hybridized, which you already know, so I'm not going to waste more time. Here you can see the sp hybridization, and 2 pi bond above and below the plane you can see, and linear structure you can expect like this one. Now as far as MO treatment, when we say 2px and 2py have one single electron which can occupy position in pi 2px and pi 2py, while we have pi star 2px and pi star 2py vacant orbital as well, and you can see here the bond order is 2, so this is 2 pi bond formed over here in the acetylenic carbon triple bond. The bonding MOs pi 2px and pi 2py are filled, while the anti-bonding, which already I have explained in the above MO diagram, where pi star 2px and pi star 2py are vacant. The pi 2px, that is pi bonding 2px and pi bonding 2py molecular orbitals are perpendicular to each other. The actual nature of bonding between the metal and alkyne in transition metal alkyne complexes is intermediate between these two extremes of the pi, and hence we're going to get these two kind of metal alkyne complex, A, where metal alkyne complex is quite similar as the alkene, while in B you can see that it is going to attach with metal N+2 metal ions in this form, and Mn plus metal ion, it is in alkyne form. So here metal cyclopropene, so cyclization would be there, and here simple alkene complex would be there. So two kind of bonding is possible in the case of metal alkene complexes. In A, there is only alkyne to metal sigma bond formation, and there is no pi bonding is there, so it is 2 electron donor metal alkyne complex. As the extent of the metal alkyne pi bonding, back bonding increases, the C triple bond C bond is lengthened, and the substituent group, that is R group, bends away from the metal atoms. when there is a complete back bonding from metal to alkyne in the vacant antibonding pi orbital of the alkyne, and alkyne to metal sigma MO mix up together to produce two sigma MOs, as you can see in the structure B, which is called the metal acyclopropane. It is doubled sigma bonding model as well in the B structure, and it successfully explain the arrangement for arrangement of CCXL arrangement in A, and in B bending of the substituent away from the metal. You have already seen in the previous slide, and the third one is the lengthening of CC bond length. So these three can be explained using that arrangement. The bonding in trans dichloro paratoluidine and tributyl acetylenic platinum 2 complex is close to structure A, because CC bond length there in this complex is 1.27 angstrom, so which is very closer to 1.20 angstrom of carbon-carbon triple bond, so hence very little stress would be there, and the tertiary butyl bond angle would be of 165 angstrom, so there is not much bent away like 140 in the case of diphenyl acetylenic group, which is close to 120 angstrom of CC bond length and 180 of the CC acetylenic linear acetylenic group, and hence it gives a kind of structure where there is two electron donor acetylenic ligand. This ligand can act as two electron donor ligand, and this is due to the fact that platinum 2 is a poor pi donor, and that is how this tertiary butyl acetylenic carbon-carbon triple bond is a poor pi acceptor, and hence it will going to give you two electron donor ligand or act as a two electron donor ligand. However, the bonding in platinum which is having the ligand triphenyl phosphine, bis triphenyl phosphine, and diphenyl acetylenic group with platinum in zero oxidation state is close to structure B, because carbon-carbon bond length, which should be 120 angstrom, is now increased to 132 angstrom, and carbon-carbon phenyl bond angle, where you can see in tertiary butyl it is 160, which is closer to 180, while here you can see in diphenyl acetylenic group it is 140. That means more bent away structure would be there and are close to 1.34 angstrom and 120 degree of the ethylenic group, that is C double bond C, and hence we are going to get acyclo or alkyne metal complex cyclopropene kind of structure. This is due to the fact that platinum here in the zero oxidation state is a good pi donor, and the diphenyl acetylenic group is a good pi acceptor, and hence you can say the structure is like B, and here you can say the structure is like A. The vacant hybrid orbital of the metal atom overlap with the filled pi MO of the alkyne molecules, forming alkyne to metal sigma bond. At the same time, the filled d atomic orbital of central metal ion or central metal atom overlap with the vacant pi star MO of alkyne molecules, forming the metal to alkyne back bonding. That is a synergistic effect, you can explain in that way. This situation is similar to that in the metal alkene complex. Here the similarity would be there, and where it differs, that already we have explained compare and contrast. So here you can see that alkyne to metal sigma bond formation. There is a vacant hybrid orbitals of metal will going to gain electron from the acetylenic triple bond, and it going to given the electron from pi b MO orbitals, and that going to form a sigma bond formation. Now the filled d orbital of atomic orbital of central metal ion going to overlap there with the vacant pi star antibonding orbital of acetylenic triple carbon-carbon triple bond. So it is from metal to alkyne back bonding is going to form, and we're going to get this synergistic effect over there. So in addition, the alkyne molecule has additional pi and pi star molecular orbitals as well, and but since the two pi electroclouds lie in the plane perpendicular to each other, it is not possible to get good overlap with metal orbitals at the same time in a mononuclear complex. However, in dicentric complex where the biphenyl acetylenic group would be present, the position of two cobalt atoms is such that both the pi molecular orbitals of alkyne are involved in bonding. So here the bicentric would be there it acts as a bridging ligand, and more realistically we can assume approximately sp3 hybridization for the carbon atom, which forms 4 sigma bond, one with a phenyl group, one with other acetylenic carbon atom, and two with carbon monoxide, because bicentric complex is there. Therefore, the CC bond distance, that is 1.46 angstrom, indicate a bond order of 1.3 and supports this viewpoint. In 1989, J.L. Templeton suggested that alkynes can also behave as 4-electron donor in a mononuclear complex as well. He labeled two field pi molecular orbitals of alkyne. One is a parallel pi and the other one is a perpendicular pi. In the following figure, which you can see that possibility of orbital overlap between the metal atom and alkyne as suggested by Templeton. So here, according to Templeton, this pi electron is parallel to the metal. So pi parallel to metal forms sigma bond formation. Here you can see that metal have filled d orbital and ligand have parallel pi anti-bonding orbital, and this interaction is going to form pi back donation. While in this figure you can see that the pi orbital, which is perpendicular to the molecular orbital, also going to interact with the vacant d pi or atomic orbital of central metal ion. So when you compare these two, you can see here this one is filled, so metal is going to give back donation to acetylene, and here you can see that pi which is perpendicular to the central metal ion, which is a filled one, and the d pi orbital of metal, which is vacant. So this kind of interaction in which pi, which is perpendicular, will going to donate electron to metal and form pi bond, and then you can see for a filled d orbital of metal will going to donate back to the anti pi perpendicular and form theta bond. So this is a theta bond formation according to Templeton, and this is how in the single, without bicentric, with the single metal center, the 2 pi orbital, which is parallel and perpendicular pi MO of a ligand, alkyne ligand, will going to interact with metal and going to act as 4-electron donor ligand, alkyne as 4-electron donor ligand over here according to Templeton. Now the vacant hybrid orbital of the metal atom overlaps with the filled pi parallel molecular orbital of alkene group, forming pi parallel to metal sigma bond, which already I have explained in the figure above. And similarly, vacant d pi atomic orbital of metal atom overlap with the filled pi perpendicular molecular orbital of alkene, forming pi perpendicular to metal pi bond. So here both these ligand sigma and pi is formed by alkyne with the same central metal ion. One is sigma, other is pi, and therefore alkyne may act as 4 pi donor ligand. The 4-electron donor role of alkyne is expected to be crucial for metals having relatively few d electrons, having vacant d pi atomic orbitals, such as molybdenum in +2 oxidation state 4d4 and tungsten 5d4 configuration. Let us consider two alkyne complexes as well over here, where we have these two complexes, complex A and complex B, and we are going to compare the electron count in it. Here electron count of a complex A and electron count of a complex B. These two example would be there. Here biphenyl acetylenic will going to give 2 electron donation, and here we consider in this biphenyl acetylenic will going to give 4 pi electron according to Templeton scheme. Now here you can see that 3-methyl phosphine that is 3 ligands are there, and these 3 ligands is going to donate 6 electron to the central metal ion, and 1 methyl cyanide will going to give 2 electron. The charge, overall charge of complex +1, so -1 electron would be there. Total 18 electron count would be over here. Gives the stability to the complex according to 18 electron rule. Now in the B complex you can see 9 electron donated by the cobalt, that is the same. Now instead of 2 here you can see 4 electron will be given by this diphenyl acetylenic ligand to carbonyl according to Templeton scheme, and 6 electron would be given by this trimethyl phosphine because 3 ligands would be there, and there is no ligand given by methyl cyanide because there is no presence of methyl cyanide in this complex B. And the charge which is -1 electron, total 18 electron. So according to 18 electron rule, these two complexes are stable, and Templeton scheme you can see over here, which indicates the 18 which going to accept the 18 electron rule or satisfy 18 electron rule as well. Now the electron count of the both the complex is 18, and in the complex A the biphenyl acetylenic act as a 2 electron donor, while in complex A and B the donation of 2 more electrons by the alkyne compensates for methyl cyanide loss, and thus biphenyl acetylenic act as 4 donor according to Templeton scheme. This is why the cobalt carbon distance in structure B is 1.85 angstrom compared to structure of complex A, which is 1.98 angstrom. So here the bond length get decreased between metal and carbon, and because the biphenyl acetylenic carbon is more tightly held to cobalt ion in structure B compared to structure complex B compared to complex A. Now let's see the properties of this complex. Relativity of coordinated alkyne depends upon the nature of metal involved in the reaction. We have reaction 1. Reaction with nucleophiles. The alkyne complexes of transition metals in higher oxidation states and cationic alkyne complexes are readily attacked by nucleophiles on the coordinated alkyne moiety. It is trans addition reaction. So this will going to give you trans addition reaction. The example of trans addition reaction. Here the example of trans addition reaction would be there. So here you can see the trans addition reaction of this metal alkyl complex. Next one, that is reaction B, that reaction with electrophiles. The alkyne complex of transition metal complexes in low oxidation state can be attached or attacked by the electrophiles on coordinated alkyne moiety. It is generally known as a cis addition. So that is trans addition, this is cis addition reaction, and here you can see the cis addition reaction and gives cis butene compound is going to be obtained by this reaction. This is another example where you can see cis addition would be there. Now the third one is the displacement reaction. The coordinated alkyne molecules can be displaced by another alkyne molecules or other ligands as well. These are the two examples for that. Now application of metal alkyne complexes. Here you can see that metal alkyne complexes are intermediates in semi-hydrogenation of alkynes to alkene. So alkyne to alkene information we can use this. You can see C2R2 plus H2 gives C2R2H2. This transformation is conducted on a large scale in refineries which intentionally produce acetylene during the production of ethylene. It is also useful in the preparation of fine chemicals, and semi-hydrogenation affords cis alkenes. Metal alkyne complexes are also intermediates in the metal catalyzed trimerization and tetramerization reaction processes. Cyclooctatetraene is produced from acetylene via intermediacy of the metal alkyne complexes. Then variant of these reactions are exploited for the synthesis of substituted pyridines. The Fuson-Khan reaction provides a route to cyclopentanones via the intermediacy of cobalt alkyne complexes. With the shift away from the cobalt based acetylene to petroleum based feedstocks, that is olefins, catalytic reaction with alkynes are not widely practiced in industry, and acrylic acid was once prepared by the hydrocarboxylation of acetylene. This is the reaction for that. And well, this is enough from my side. Thank you very much for paying attention to this video lecture. Keep asking questions. As you know, asking question is a beautiful way to gain knowledge. Thank you.